All right, let's talk about electric fields. This is a kind of a small topic in this class, and we're really only going to hit the very tip of the iceberg of it. To start talking about it, just a review of static electricity, very simple things. You know that there are two electrical charges, one is positive, one is negative, and we know that like charges repel and opposite or unlike charges attract. So if you have two positive charges, they're going to repel each other. Two negative charges are going to repel each other. But if you have a negative and a positive, they'll experience an attractive force. So that's what these are. And we know that those protons in the atom are the positive charges, or they contribute the positive charges, we should say. The electrons are the negative parts of the atoms, and neutrons are neutral. They don't really play much of a part in this. And the whole point with charges and electricity and electrostatics is that objects can transfer their electrons. Electrons are the big deal. That's why this is called electricity. Outer electrons get transferred from one atom to the next. However, protons and neutrons do not move during electricity. You can move protons and neutrons with atomic reactions. We'll talk about that later. But you've got that strong nuclear force that's in the nucleus that holds those guys in. Therefore, those guys are the only things that are going to move. So let's move on and talk about electric fields. An electric field is a concept that we talk about because it's easy to understand that if you have two charges, I can draw these two, something like this. It's easy to understand that if you have two charges, one here and one here, we understand, for instance, if these are both the same charge, they're going to experience a repulsive force. We get that. But what's different is that we can take one charge by itself and understand that there's a three-dimensional force field that goes on all around this charge, because you can place any positive charge anywhere around this and it's going to repel in a direction that's straight away from that charge. And so electric field line is a vector that relates the force exerted on a test charge to the size of the test charge. Now this term test charge is something that you need to know. You need to know that in this class, test charges are always positive. We talk about positive test charges. So a field line relates the force exerted on the test charge to the size of the test charge. Talks about the direction of the force and the magnitude of the force. Another word for size is magnitude. Field lines demonstrate how force affects things a distance away, because as you remember from what we talked about with Coulomb's law, the further away a charge is from something, the less affected it'll be. The same with gravity. The further away you are from planet Earth, the less you'll be affected by Earth's gravity, or by Earth's gravitational field. An electric field is really no different. So we're going to draw an electric field map. It's a diagram that shows the strength and direction of an electric field, and it'll look something like this. If we have a positive charge in the middle, the electric field will always point away from a positive charge, and we'll talk about why in a second. Here's what it is. By convention, the direction of the field is always away from a positive. You might want to underline that. And it goes towards a negative charge. And the reason comes back to this positive test charge. All right. Imagine that there's some charge in the middle and it's held there in the field that we're talking about. And a positive test charge says, okay, we're going to drop some test charge. Let me change colors here. How about blue? We're going to drop some positive charge somewhere in this field. And the question is, what's the effect on this charge because of the presence of this one? Well, obvious, if they're both positive, this is a positive test charge, not negative. This test charge is going to go away from the positive charge. It's going to be repelled, and it's going to be repelled in a direction that is directly away from it, on a line that connects the two, a straight line through the two. That will be the direction that this positive test charge will go. And so that would be the direction of that test charge at that point. Therefore, that's what the field would be at that point. And we can drop a test charge anywhere in here, and we can do the same thing and realize that these field lines, just as is shown here, are going to always point away from this positive charge, because any positive charge dropped anywhere in here is going to move as quickly as possible away from this positive charge. The closer you are to this charge, the quicker it's going to move, because the stronger the force is. The strength of the field is indicated by the closeness of the line. So as you can see, the closer you go to the charge itself, the lines get closer together, And then as we move out, the lines get farther and farther apart. That indicates the relative strength of the field. As we said, the further away you are, the less affected you'll be. Farther away you go from this charge, the less, the weaker the electrostatic force is going to be. So electric field diagrams look like this. This is the one that we saw on the previous slide. This is electric field of one positively charged object. All the lines point away from it. But then they can get a little bit more complicated. We come down here to something like plates. Again, lines point away from a positive and towards a negative. So you'll notice that all these lines have arrows pointing toward the negative charge. So any positive charge that's placed in here is going to follow the direction of these arrows. And interestingly, if you place a negative charge in here, it's easy to see that that negative charge will do the opposite. All right, that would be what a negative would do. But then if we come up here to these two, these are the ones that are interesting that you're going to need to know. When we place two spherically shaped objects in a field and we give them electrical charge, the field mapping of those two is very interesting. And they look something like this. You need to kind of memorize the shape of these field lines because you're going to see them later. Where's the field stronger? Think about that question for a minute. Look back at your notes. And the answer is the field is stronger closer to the charges because remember, again, closer the lines are, the stronger the field is. Where's the field weaker? Farther away from the charges. And also you can say between the two charges is a weak field because the lines are pretty far apart right there. You put a charge right here. If it's exactly right in the middle, it actually may not do anything at all. But let's look at and draw some electric fields. By the way, if you look at the back side of your notes that talks about calculating the strength of an electric field, that's this stuff. We're not going to talk about that in this class. So the entire back of the notes, if you have those in your hand, you can completely cross those out.